So this is on Newton's first law of motion, chapter 4 in our textbook. Newton's first law of motion is also called the law of inertia. So some history. Aristotle way back when, back in the 4th century BC, this is like over 2,500 years ago, something like that, the world was not, very well defined. And so Aristotle came up with the idea that all motion is broken into two categories: natural motion and also a violent motion. Natural motion is basically the natural order of things. Like, for example, if you put a round object on the top of a hill, it'll roll down, and that's natural. And what violent motion would be if you were to take that rock and you throw it. It's not natural because you're throwing it, and so therefore it's a force or some sort of motion that's a result of being pushed or pulled. So then a force then causes an object to move against nature. Like if you were to lift something up, things naturally want to go down because of gravity, but they didn't really understand what gravity was. Just that's how naturally objects behave. And so when you move it away from that kind of a motion, then it's a forced or violent motion. Not really, being tested on, but just kind of good to know. So most thinkers at that time had a pretty false assumption about what motion is, especially on the planets. So motion back then was not talking about how you and I would run, whether a cart was being driven by a horse and that kind of motion, but a lot of motion was debated on the motion of the stars and planets. So then now we go, fast forward into the future, into Copernicus. And Copernicus, he's, from a wealthy family, but at that time, his ideas of motion was very controversial. And as you probably have remembered from your history classes, that the church had a huge impact on how policies were made and what law was. And so at that time, when he developed a theory on Earth and how Earth was not the center of the universe, and that we on Earth are revolving around the sun, whereas before it was thought that the sun and all the other planets and stars revolve around Earth. And so when he kind of gave this theory, he was persecuted, and he was, basically on house arrest. And because he's wealthy, he wasn't sent to prison, but he was persecuted because of his beliefs. He did, however, because he was wealthy, he did have books published. Now, a lot of the books were collected and, burned or whatever they did at that time, but for the most part, word didn't really get out, except for a few books. And because they were published on his own, he didn't get, government support or any other money from other sources. He was able to produce a few books from his family, from the money in his family, and it did go out. And so as it went out to the scientific community, more and more people started to understand what he was trying to say and agreed with him. So over a long period of time, people started thinking, oh, okay, well, in that case, it seems to make sense. And the scientific community was now ready for his forward way of thinking. And so Galileo, who lived close to the same time period, supported his theory on planetary motion. But in addition to that, he went on ahead and thought more about motion, more on Earth and on everyday things. But again, because of his way of thinking, he was also persecuted, and he was essentially deemed as a lunatic. So he was not around for a very long time. He also have talked about what forces are, whether it's a push or a pull, and but he brought into the concept of friction, which is very interesting because friction was never thought of as anything else other than just the way things are. But what he discovered about friction is that friction prevented things from moving. And then if there was friction, that in order to keep that object moving, you would have to continuously push or pull something in order to keep that object moving. So, however, if for some reason we are able to eliminate friction, all motion will not require any forces to keep it moving. So, things become more efficient. So now, if friction could be eliminated, if you notice over here, this ball, if I were to let it fall on this little ramp, it'll roll down and roll back up to the same height. And over here is a similar idea, even though this side is steeper and this side is not as steep. If I let go of a ball, it'll roll down and it'll roll back up to the same height. So then, essentially, we're talking about the amount of height that the ball will roll after it has been let go, if we could eliminate friction. However, what happens if I have a ramp here but no ramp on this side, just completely flat? If that was the case, then the ball rolling down on this side of the hill will roll down to the bottom of the ramp, and it will just continue rolling parallel to the surface. If there was no friction, it will continuously roll and roll and roll forever and ever, and it will never stop. Okay. Only time it would stop is if there was something else blocking it, providing a force to stop the ball, or if somebody went ahead and stopped the ball with their hands or something. So now, looking at inertia, because the whole idea of Newton's first law came from this concept of inertia. Now, it was defined that inertia is basically the resistance of an object to change its state of motion. So if something has more inertia, it'll be more resistant to motion. So if something was like has a high state of inertia and you want to move it, it will take you a lot more effort to move that object. So here I have a little cartoon where I got a truck, and if you notice that there is a ladder on the top. The ladder originally over here is moving, and the object, that ladder, has inertia. And because it has inertia, it is going to continuously move forward because it refuses to change its state of motion. It's already moving, it wants to keep moving. So when the truck hits the car, the ladder wants to keep moving, so it flies forward. It resists a change in its motion. Its original state of motion was moving, it wants to keep moving. And so this little cartoon shows that it doesn't want to stop, it wants to keep moving. So here comes Newton. Okay? Newton says that every object will continue in a state of rest or of motion in a straight line at a constant speed unless it is compelled to change that state of motion by forces exerted upon it. Sounds kind of confusing, so Galileo reworded it. Okay? For objects at rest will remain at rest, object in motion will remain in motion unless an external force acts upon it. So that's basically what Galileo said. Now how are we going to apply this? So here I have a sports car, and a dude is basically sitting inside of the sports car, not wearing his seatbelts, of course. And so as the sports car hits this brick wall, the car stops. Now, this dude inside, since he's not strapped in, he is going to continue his state of motion forward and be ejected from his car. That's basically what happens when you don't wear your seatbelt. Okay? So that's Newton's first law of motion. Now, what is inertia? Inertia is basically a way to measure mass. Inertia is the equivalent of mass, if you want to put it that way. The more mass you have, the more inertia you have. So, what is mass? Mass is the amount of stuff that an object has. So, like the atoms and molecules that made up this object, this mass. That much stuff, that much atom or molecule is basically what mass is. So the more mass an object has, the greater inertia the object will possess, and then it will require more force to change its state of motion. So if you have a little mouse and you have a big elephant, and you want to push this little mouse, just kind of push them, just one little pinky, you can push this mouse all the way across the tabletop. Whereas this elephant will require a lot more force for you to push it. You can push as hard as you want. If the elephant doesn't want to move, it probably won't move. So now, the difference between these two animals would be the fact that the mouse has a lot less mass and the elephant has a greater mass, which means that the mouse has less inertia the other one have a greater inertia. So based upon your experience in pushing or lifting or pulling heavy objects, which will require more force for you to move those objects, something light or something kind of heavy. So then now you have to understand that mass is not a volume or weight. Okay, volume is how much space something takes up. So something that's very, very heavy does not necessarily have to be very, very big. And volume is measured in liters or cubic meters, cubic centimeters, something like that. And what weight is the measure of the gravitational force acting on the object. So something that's has a lot of weight, it correlates with how much mass something has, but the weight is related to the force, the gravitational force on the object. So weight in science and physics is measured in newtons, and it's capital N, and it is kilogram meter per second squared. That's the units for newtons. Okay, so Newton is a derived unit where it derives from kilograms meters per second squared. Now, weight is proportional to mass, and it depends on where the object is located. So if it's located here on Earth, then it will be weighing a little bit different than if that same object is on the moon. Okay, so on Earth it would be heavier or it would be lighter. On Earth, would it be heavier or would it be lighter? So, depending on what you know of Earth and the moon, you'll be able to determine what the weight is. So how you calculate for weight is you take the weight of the object is calculated by the mass times the acceleration due to gravity. So mass is always measured in kilograms. Acceleration due to gravity is always measured at meters per second squared. So you multiply two values together and you'll get this unit called newtons. And that's what weight is. Another example for weight is pounds. You'll be weightless. You'll be 0 pounds in space because there's no gravity pulling you down, so therefore there's no acceleration due to gravity. So you just have 0 weight, but you have mass. You still have mass because you're still made up of atoms and molecules. So you will have mass regardless where you go, but the amount of weight you have is dependent upon how much gravity there is at that particular location. Okay, so this will conclude part 1 of your screencast. We'll be recording screencast number 2, and you will be hopefully watching that.